Hi guys, in this video we're going to talk about similar figures, specifically proportional polygons. We're going to talk about what a proportion is, then we're going to cover 5 different examples. So let's get started. If I could keep it simple, all a proportion is a fraction equal to a fraction. So I could say 3 over 5 is equal to 6 over 10. The reason why they're equal is because I could reduce 6 over 10 to 3 over 5, making them the same. Equality is one of those mathematical concepts that often get taken for granted. When that equal symbol is there, or equal sign, it is true, even if it doesn't look like it is. So here, I could take this 5 and multiply it to the 6 and get 30. And I could take that 10 and multiply it to the 3 and still get 30. So there's a number of ways to show that equality exists between these two fractions. Let's look at a couple of ways we could set up proportionality amongst these two triangles. Okay, so I took a second and I color coded the sides of these triangles. These two triangles are similar. Part of the reason why I know they're similar is because if you look at the coordinate letters, or the vertex letters, the points are labeled A and A prime, C and C prime, B and B prime. That indicates that the smaller triangle is a pre-image and the larger triangle is an image. Or in this case, the triangles are dilated and the scale factor between them is 3. So in other words, triangle A prime, B prime, C prime is 3 times larger than the smaller triangle. Alright, let's play with a couple of proportions. So the way I set up the colors is to indicate corresponding sides. And what I did here is I created a proportion with sets of corresponding sides. So I did 2 orange sides on the left and 2 blue sides on the right. Now I'm going to cross multiply them. So at first glance, when we look at these, they do not look equivalent. 9 times 5 is 45. Then 3 times 15 is also 45. So even though we don't see the scale factor in this proportion, these fractions are still in fact equal. Let's take a look at one more example. Okay, so this time what I did is I put 2 red sides on the top and then 2 blue sides on the bottom. It's a little bit different than the way I set it up last time. This time the scale factor is a little bit clearer, but when I multiply this, so 5 times 12 is 60. Then 15 times 4 is also 60. In this particular case, I could have also reduced this fraction to 4 over 5 by dividing both the numerator and denominator by 3. The strength of proportions is that you could set them up in multiple different ways. Proportions are a very powerful tool to know in mathematics. They are applied in many fields, from cooking and finance to mechanical design and engineering. In these examples, we're just going to cover some basic examples of proportional shapes. Alright, let's get started. This is how most math curriculums cover proportions. You have to be careful here. Because of DE, which is x minus 5, oftentimes it becomes difficult for us to see the equality that exists within a proportion. A couple of tricks we can do. So what I'm going to do is label the letters provided to me 1, 2, 3 of the triangles. 1, 2, 3. Now, that symbol in the middle here means that the triangles are proportional or the triangles are similar. The order of the letters is very important. It's indicating the corresponding angles of the triangles. So what I am going to do is I am going to number these triangles. There's quite a number of tricks on what I'm about to do. Some people like to draw shapes around corresponding parts. Other people like to use highlighters, like to use colors. I'm going to just use these numbers. Not suggesting that it's stronger or weaker than any other approach. If you can find success in this in your own way, you should absolutely pursue that method. So, the way I could set these up, if I call this triangle A and triangle B, I could set up this proportion in a couple of ways. I could set it up this way, where I have two parts from triangle A and triangle B, or I could set it up where I have corresponding sides on top of each other. The most important thing I could do is make sure that I'm consistent in my order. So, because I'm going to start in this case with my term with my variable in it, I am going to pick the other triangle. So I'm going to pick 27. Then I have to pick my two remaining pieces. Okay, let me just take a second and clarify what I did. I set this one up, triangle B over triangle A, then triangle B over triangle A. But in doing so, I also set it up, and this is where we have to really be paying attention. 2, 3, 2, 3, and 1, 2, 1, 2. So there's kind of quite a few things here that you have to be on top of. Alright, let's cross multiply and solve this. So I cleaned up the space a little. And what I'm going to do is I'm going to reduce this fraction on this side. You can sometimes reduce the other fraction, but I cannot do that here. Students often ask me, do I have to reduce? And the answer is no, I don't. But in reducing, now I do not need a calculator. When we're cross multiplying, I got to draw my little arrow going this way, and you take a number like 3 or a constant, if you want to be technical, and multiply to an expression, you have to place that expression in parentheses. Now what I have to do is I have to make sure to distribute that 3 to both of these terms, which now allows me to solve it like normal. Normal meaning that I start to move my terms away from x. So in this case, I am adding the 15 to create a 0 here. So that way that 15 does not affect this side of the equation, but I have to add it to the other side. And if you're saying to yourself, wow, this guy really knows his numbers, the answer is, nope, I paused it and used a calculator. Now I am dividing the 3 away from the x because 3x is multiplication. The operation between the 3 and the x is multiplication. And I want to create a 1 in front of that x. The only way I can do that is through division. And the reason for that is because 1x is what I want. I want to know what 1x equals. And 42 divided by 3 is 14, according to my calculator. Okay, let's take a look at the next example. In this example, we have a similar polygons. Now, I definitely feel that similar triangles should be more of a focus than similar polygons, but these pop up all the time in math curriculums. The easiest way to do this is to kind of figure out which sides correspond. In this case, and thankfully, the orientation is the same. If you're watching this and you're not one of my students, you would know I do not like giving students these when the orientation is different. Sometimes the sides are very similar to each other and it could become really hard to tell them apart. The easiest way in this case, if the orientation is different, is to kind of just judge it by size. Or we can notice that we have 42 and 42 and 35 and 35. Those sides probably correspond. The blank sides probably correspond. So that means the 6x and the minus 6 corresponds with the 36. Alright, let me set up this proportion. The way I'm going to set up this proportion is I am going to set it up as 35 over 42 equals 6x minus 6 over 36. I could have set this proportion up in a number of different ways, but what I did is I took the time to figure out what is the easiest way to set this proportion up. And the reason why I chose this combination is because every part of this proportion can be reduced. So let's take a look at that. I made in the past a big deal about good calculators, and good calculators with math print are priceless for the few extra dollars that they are. You're often comparing a calculator that's $15 that does half of what a $20 calculator would do. In this case, the calculator tells me that 35 over 42 will reduce to 5 over 6, or is reducible by 7. The other side is also reducible, but you have to be careful when you do this. So I can actually reduce each term by 6 because 36 is divisible by 6. This is super convenient. I don't always recommend this because it's very easy to make a mistake. But if you want to explore and try different ways of solving math problems, you can reduce that 36 and the 6x minus 6. The same rule that applied here on the previous example here, where I had to distribute in multiplication, applies here where I can distribute in division. Now let's cross multiply and solve this. While I'm no massive number aficionado, I can now multiply this or cross multiply this without a calculator. Then I'm going to distribute. That's 6. Coincidentally, and I do mean coincidentally, I ended up with what I reduced out before. But here, I have these such simple numbers. I'm going to add the 6 to create a 0 here. That 30, which looks like 3 triangle, is going to become 36. Then I'm going to divide out this 6 to create a 1 in front of that x. I do not like the term cancel out. I think it is misleading and it's suggesting that something doesn't exist anymore. We want to know, or we want to keep track of, why we are changing the operations or finding these reciprocal or inverse operations as we solve. And the reason for it is we want to maintain equality. So if you want to do a check here just for the sake of it, I could actually plug this in, and I'm doing this live without a script here, but I'm going to plug that in. So I plugged in 6 into that x, that's my plug, and 6 minus 1 is 5, so I got 5 over 6 again. So that's a check. I'm not a big advocate for checking, but in this case, I just want you to see, because it is so difficult to see, that equality has been maintained through the entire process. And we found the missing element so we can complete the proportion. Alright, let's do one more example. And by one more example, I mean 3 more examples. Okay, so let's start to kind of hustle through these. I see here that this is the short side. Then I have this diagonal looking side here. It's probably the longest side of the triangle. And that's what corresponds. Once again, I'm kind of making a plan, trying to figure out how I could set these up so these reduce a little nicely. And really what bothers me is that 24. So I'm not very good at 24 times tables, so I'm going to avoid using it. And the way I'm going to do that is I'm going to set up my proportion 9 over 24 equals 6 over 3x minus 2. The 9 over 24 will reduce to 3 over 8, which is a whole lot friendlier than 9 over 24. I really can't reduce this 3x minus 2 with that 6 over it, because not every term is divisible by the same thing. So we're just going to keep that there. But it's still an improvement from what it was. Now I'm going to multiply 8 times 6, which is 48. Then I'm going to multiply the 3x minus 2 times the 3, placing it in parentheses again. And now I have to distribute. I do hope the use of these different colors is kind of helpful in presenting the solving process. The solving process is amazingly difficult for students to learn. Those of us that are fluid in math, which I'm not really one of them, take for granted how difficult it could be for somebody to learn this process. So once again, I am turning that -6 or that -6 into a 0, so it does not affect that side of the equation anymore. 48 plus 6 is 54. The 9x. The 9 is multiplying the x. I need it to become a 1, so I'm going to divide. And x equals 6. It's a little bit late in the day, and it's actually about 9:30 while I'm recording this video, and I'm very tired, so I'm relying on the calculator pretty heavily here. Make sure when you do this, you have a calculator next to you. I personally do not agree with a calculator being a crutch, but it is a helpful tool to make sure that you are not making a mistake. Alright, let's take a look at two more examples. Okay. With the next two examples, I just want to compare some bow ties. So we're going to number these letters the way I did in the first example. And I'm going to label the letters on each triangle. And doing so is really critical. We will see when we compare the two examples, but in this case, if you look, this side corresponds with this side. And then, so the way I'm going to set this up is I'm going to set this up where I have 9x plus 15 over 40. Then I'm going to have 120 over 50. And I'm going to do my very best to reduce this, though that doesn't look like it's going to happen very much. Alright, let's take a look at what I got. So, for starters, a couple things to recognize. When I set up this side here, that kind of dictates how the other side is going to go. Since I set this up with the 9x plus 15 on top, then the 40, so I went in this direction, let's say. That means I have to go in that direction that way to set up the proportion, if that makes sense. So now I'm going to reduce this to 12 over 5, which isn't that super friendly, but thankfully I have a calculator. And let's see how we do here. So I'm going to cross multiply. That's going to be 5 parentheses 9x plus 15 equals, let's see what 40 times 12 is, and that is 480. And now I'm going to distribute. So 5 times 9 is 45x. 5 times 15 is 75. 480. I'm going to subtract the 75, create a 0. So this way it no longer affects that side of the equation. Be careful, as I almost just did. Do not lose your signs. It's a very common mistake. 480 minus 75 is 405. And now I'm going to divide by 45. And let's see what x equals. And x equals 9. Okay, let's take a look at the next example. And the last example. So let's see what happens here. 1, 2, 3, then 1, 2, 3. Now I'm going to number my triangle. 1, 2, 3. I'm going to number the other side. 1, 2, 3. When I look at my corresponding sides, 1, 2, this side here corresponds with this side. This side here corresponds with this side. So, in the previous example, the bow tie was twisted. In this example, the bow tie kind of folds open. Numbering and recognizing your corresponding parts is the most important thing you could do here. That's a trap that you could fall into very easily. Alright, let's set up this proportion. Once again, I'm kind of cornered and I cannot reduce a whole lot, but I'm going to look for every opportunity I can to make this problem easier. So because I started here and I went to there, that means I have to start here and go to there. Be careful not to swap or flip the proportion. If you do so, you will get the problem wrong. So let's take a look at the left side first. I noticed that everything is reducible by 2. So I'm going to do that. 34 divided by 2 is 17. X minus 1 over 36 divided by 2 is 18. Not super friendly, but maybe better than what it was. Let's reduce the other side. The other side reduces to 14 over 3. And now I'm going to cross multiply and solve. Reducing or simplifying fractions isn't always the most helpful thing to do. I didn't know how this problem would reduce prior to punching it into the calculator. But I am definitely dealing with smaller numbers than I would be otherwise. Now I'm going to distribute, and 3 times 17 is 51. X minus 3 equals 252. Another thing to be careful of. So I am genuinely getting nervous that this might not work out and I might have to go back and edit this. But with these big numbers, it's hard to see the solution coming out. Definitely when they're odd numbers like this, like 252 and 51. It's hard to kind of predict what's going to happen, so you really have to let the math do the job. And if there is a mistake, then you have to go back and just try to figure it out. So now I'm going to divide out the 51. And let's see what I get. So 255 divided by 51 is 5. So I'm pretty sure I got the right answer there. If you make a mistake here, it's really hard to diagnose it. So what my suggestion would be often is to start the problem over all the way back to here, where you label your sides. And then as you get more experience, you should be able to start finding your errors. Alright guys, I hope this video was helpful.